Hi. A student asked me about the castellated beam, and this is the method that engineer increase the load carrying capacity of a beam. By castellated them, castellated means the beam has opening, hexagonal openings, and or cellular beam, which has circular openings. I explain this increase in load carrying capacity by a simple example, step by step. Assume we have a cantilever beam under load P, which is equal to 10 kilonewtons. Then this end is fixed, A and B. This is like a dive in a pool, and we wanted to design it. And the more governing stress here that we have is a horizontal shear stress or bending stress. We must increase the load carrying capacity for bending stress and then do something about the horizontal shearing stress in the next video. I calculate the bending moment first. In order to find out where the bending moment is maximum, you have to draw bending moment diagram, which here, if this span is 3 meters, then this is minus 30,000 Newton meter. Here, point origin. Here is the axis X. And this is the bending moment diagram. And this is the maximum bending moment happen at the base, here at the origin. Then, you know how to calculate bending stress. Famous formula, sigma max is equal to when bending moment is max, when distance from the neutral axis is max, and I of the cross section of the beam. Assume that moment inertia of this beam, I consider a beam here, which is a standard I beam, S 180 times 30. 180 is the nominal size of the top flange to the bottom flange. Top surface of the top flange, bottom surface of the bottom flange is 178 mm. And width of the flange, 98. Thickness of the flange is 10 mm. And thickness of the web is 11.4. And I for this beam, if you calculate that or go to the table, you will find out this is 70.65 10 to power minus 6 meter to power 4. Then, if I substitute these values here, I will find out that 30,000 Newton meter times 178 divided by 2 10 to power minus 3 meter, I is 70.65 10 to power minus 6. You will find it is 151 10 to power 6 Pascal or 151 megapascal. Let's say it's 150 megapascal. Okay, this stress is high. I wanted to decrease this stress. What I wanted to do, by increasing I, you can decrease the stress. How I can increase I? Castellated beam? Yes, it's the one of the method. Then I consider this beam and I give it to machine. Machine cut into 2 pieces. And then I separate them. Top surface is like that. And the bottom one also is like that. You got here I shift one of the parts, one actually opening forward or backward. What I have, I move this part to here and cut the rest of the beam. Then I cut it, I separate into two pieces, and then I move this part to the top and make it like that. And I continue. And I then again welded this part together. What happened? The depth of the beam is increases without increasing the weight, without increasing the price, because engineers don't want to buy a larger beam which is more heavier and more expensive. With the same budget for this beam, we can make a larger beam and increase its load carrying capacity or bending stress capacity. Okay, let's I show you how. Let's get rid of this drawing. Then the only change here is that I cross section, for example, if it is 180, change to 270 normally. But the ratio is 1.4, 1.5, and it depends on the cut machines and every size of opening and everything else. I use 1.4, and 1.4 make this flange to flange depth of the beam 249.2. 250, you can say nominal size 250, okay? And if you calculate the same width 98, the same thickness 10, the same thickness 11.4. But if you go to the table, you will find the 250 S250 beam has no this web thickness, larger. Web flange width, larger, 133 for example. This is 30 millimeter, 1.3. And then it is completely different. You cannot go to table, okay, I change it to a beam 250 and then I take my moment of inertia from the table. No, you must calculate it yourself because everything is the same as 180 except the depth of the cross section of the beam. Okay, I calculated I for that and it is equal to, I think, the 47.6, 10 to power minus 6 meter fall. Then I increase I from 17.65 to 47.6. Then what happened? Stress is reduced. Remember something. Y also is increased because Y is what? Y is half of the depth of the beam. This is Y max. This is also Y max. And Y max here is larger than 1. But this increase is not as much as the increase in I. Then if we substitute a new actually value here, the load is the same. This Y is changed to 249.2 divided by 2, 10 to power minus 3 meter. And this changed to 47.6, 10 to power minus 6. And you will find out the stress is 78, 10 to power plus 6 Pascal or 78 megapascal. What happened? Stress before was 150 megapascal. Then I reduce it 1.9 times to 78 megapascal. In other words, I can use larger load on this beam to reach to 150. I can increase a max to actually for this beam to reach to 150 megapascal. How much? 1.9 times. Then 10 kilonewton can be 10 kilonewton can be approximately 20 kilonewton. What I did, I increased the load carrying capacity of the beam. This is called opening, when the opening is hexagonal, is called actually the castellated beam. And if the opening is circular, you cut it like that, then you move, and then you make a beam, separate them again, shift one actually opening back or forth, and then your beam is like that. Okay, just a second. This is called cellular beam, circular opening. The same story. You increase the depth of the cross sections and you increase the I, and also you increase the Y max, actually half of the depth. And you decrease the stress, or you can increase the load, and this is how you increase the load carrying capacity. But there is a but here, and I explain it in the next video. The but is there. Then when you when you do the opening here, you know that in neutral axis distribution of bending stress is like that. If I draw the bending stress, this is neutral axis. You got the maximum here for this example, tensile, and for this example, compressive. They come to the neutral axis, and neutral axis bending stress is 0. This is why we are not worried about the neutral axis of the beam. The meat of the beam is not here, because stress is there is 0, but the but is here. Horizontal shear stress is maximum at neutral axis, and this makes the beam weak against horizontal shear stress. What we must do about that is the subject of the next video. Thank you for watching.